Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video newsletter, well, I'm going to answer a comment that I've had about CPK from VJ. So what VJ is asking me about is why we ask for CPKs at the higher levels. So his question is slightly broken, so he's got a little bit of broken English, but I think what he's asking is, we have the 1.33 limit that lots of people ask for, we have the 167 that people ask for, and I think what he's saying is, well, why do we go above that? So the question essentially is, why do we have why the higher CPK requirements? So that's what we're going to talk about. The CPK. Why do people ask for above 1.33? Why don't they stop at 1.33? Well, this goes to the heart of the normal distribution and the ability of your statistical tools to see movement in your processes. So let's just sketch the normal distribution. So we've got the normal distribution, which is always said to be 3 standard deviations in one direction, 3 standard deviations in the other direction. Now there is the picture, and because of the nature of it, there's very little data here out at the tails. So if you were taking data points, and remember, as an operator, as a technician, as an engineer, you never see the normal distribution. What you see are individual data points. So you see this individual data point appearing on a graph. And the graph, of course, is telling you what the process is doing. It's trying to tell you whether the process is centered. So if you're trying to hit some target, it's trying to help you to see if the process is centered, etc. Well, because of the rarity of the data out here, if this process moves, if it moves over here, the data that's going to be in the tail, these data points are rare events. So it's very unlikely they're going to appear on this graph. Now, people much more intelligent than me have looked at this, and one of the things that they've said is, to be able to see a movement in the normal distribution with some certainty, sort of 95% precision, the standard deviation, the distribution would have to move by 1.5 sigma. So this thing would have to move off the center here, and it would have to move to this point here. So in other words, all of that, this is going to move to here, and all of this data here is going to be sitting out at the tail. Now that's quite a lot of data, and what we're saying is, in order to be certain of getting a data point out here somewhere, we're going to have to push the tail quite a long way. We're going to have to push it 1.5 sigma for it to really show us something unusual on the graph with some certainty. It's not saying it wouldn't do that, but we want to see it quickly with some certainty. And so the idea that the process has to move by 1.5 sigma before you would actually see it with some clarity that that's what's happened to it. Now, if we think about that in relation to the 133, 167, or even asking for a CPK of 2, which is of course up at the 6 sigma level, what does that mean? Well, let's draw some diagrams of those three scenarios. So if we go, let's have a look. 1, 2, 3, 4. Okay. Okay, so what I've done, I've got a tolerance. This is the lower specification limit. This is the upper specification limit. And what I've done, this is a 1.33. 1.33 CPK. And what that means is it contains 4 standard deviations. So if I draw, let's draw a distribution in there. The distribution, of course, would cover plus or minus 3, and there would be a standard deviation spare here. Now this is the 133. Now what, of course, what we're saying over here is if this started to move off center, either way, off center, it would have to move by 1.5 sigmas before we would have some certainty of seeing what exactly is happening, which would mean this tail, of course, if this moves 1.5 sigma, this tail is going to be sitting out here. It's going to be producing quite a lot of defects before we even see that we've got a problem. Yeah, because of course the sigma here is quite large as well. Bear in mind, it's moving 1.5 sigmas. It's not moving by a unit of scale. It's moving by 1.5 standard deviations. So these standard deviations, of course, are quite large. So when it moves, it's gonna move a long way before we see it. This tail is going to be producing defects. If you've only asked for a 133 CPK. Okay, so let's draw one now, which is 167 CPK. So we'll put the same specification limits in. So there's the same specification limits, there's the midpoint. Now what we'd have is this thing wouldn't be divided up 4 either way, it's going to be divided up 5 either way. So let's have a look. That's 5. There's 5. Now this is a 167 CPK. So now we draw in the normal distribution. So we keep the colours the same. We draw in the new normal distribution. Okay, now you can see it's slightly smaller. The sigma is smaller as well because it's a sort of 25% smaller. So the sigma is smaller. There's more room here. So of course we have room. What do we always want room for? This is room for the variability that of course you can't control. You can't control everything. It's very difficult actually for a technician to center a process accurately because he's using a graph to do it rather than a picture to do it. So the likelihood is your technician isn't quite going to have this centered. So we want some room. Now instead of having a 1 sigma room, we've got 2 sigmas of room. So now if the process moves by 1.5 sigmas, what would that mean? Well, this tail of course would be just short of that bottom, tolerance by half a standard deviation. Okay, so obviously this distribution does keep going. Statistically it keeps going, it never touches the line. So there is some danger that we might still get some defects out there because we're only half a sigma potentially away from that bottom or top tolerance. So let's think now what 6 sigma looks like. So let's draw the same tolerances. Now what we've got is a CPK of 2. So now what I've got to do is I've got to split this thing up 6 either way. So let me split it like that first. So now the distribution is only going to fill, of course, half the tolerance. So you can see that distribution is getting smaller. Now this thing, of course, is going to move by 1.5 sigma before we can guarantee that we're going to see the shift. That's what this is about. It's about guaranteeing the ability to see the shift. Now, of course, because my sigmas are smaller, first of all, the distribution isn't moving as far. That's the first thing. But of course, the other thing is it's a smaller distribution in and of itself. So now look, when it moves 1.5 sigmas, the tail is going to finish there. It's going to finish 1.5 sigma shy of the tolerance, which is, if you look here, this distribution here was only 1 sigma shy of the tolerance. This 6 sigma distribution down here, even though it's shifted, is still producing less defects than the 133 up here. And we're pretty much guaranteeing that, you know, if this thing moves, and if it moved further over here, for instance, where it's still not going to be producing defects, if it moves all the way 2.5 sigma, we're definitely going to see that. And that's what this is about. Why do people ask for the higher numbers? Because you're using statistical tools to try and tell you. When I draw these pictures, it's very easy to understand when you see the distribution and you see the whole distribution moving left and right. You see the distribution moving in and out. Everybody can understand the pictures, but that isn't how you control a process on the shop floor. On the shop floor, you never see the distribution. You only ever see the graphs. Of course, SPC charts, what are they trying to tell you? Well, an SPC chart, if it puts control limits in, what it's trying to communicate to you is what this distribution looks like. That's what the lines mean. That's the middle. That's the lower point. That's the upper point. That's the lower point. And so it's trying to communicate the 3 points on this distribution. So an SPC chart is fundamental to being able to see these shifts. And the SPC chart won't guarantee to be able to see it until it starts to move by 1.5 sigma. So in answer to your question, VJ, why do we ask for the higher numbers? Because we want to be certain that we're going to be defect free, because we can't keep 100% inspecting everything. That's a very expensive thing to do. So we sample. The sample is going to tell us what's happening. If what we've got is good CPK, we can guarantee that we've got 0 defects without having to 100% sample. And that's why we ask for the higher CPK values. Now, of course, if you want to know more about these kinds of theories and other things about Six Sigma, you can go and buy my book, which is called Drink Tea and Read the Paper. I will leave a link in the comments below for you. Otherwise, please subscribe to my channel. Click on the like button as well, because it helps with the channel. And if there's anything else, if you want to leave a comment, you want me to make a video about something, specific subject that I haven't covered, if you want to argue with me about some of the points I'm making and you want to improve the conversation and come up with better solutions that I'm suggesting, please do that as well. We're all discussing this and trying to make this subject clearer for everybody. I'm happy to make a video on any subject you wish, discuss any point you raise. So please leave some comments, please ask some questions, and I hope to hear from you soon.